Hello, my name is Martin Pirjanloo.
I'm Sam Ostrom.
And I'm Celeste Padilla.
All right, we're designing a gearbox with an input power of 60 horsepower and an input speed of 2400 RPM. Output speed was chosen to be 105 RPM. Using the ratio of the input speed and the output speed, the gear train ratio was found to be 7/160. A spare gear with a pressure angle of 20 degrees was chosen. Using the gear train ratio and the pressure angle, the number of teeth was calculated. For gears 2 and 4, the number of teeth was found to be 16 teeth, and for 3 and 5, it was found to be 77 teeth. Using the gear teeth ratio, the speed for gear 3 and 4 were found to be 498.7 RPM. For gear 2, which is also the input speed, it was calculated to be 2400 RPM. And finally, for gear 5, which is the output speed, it was calculated to be 103.6 RPM. This is within the acceptable range of 100 and 110 RPM, which was given as a design requirement. Using the equation of power over angular speed, the torque for gear 2 was found to be 113.3 foot-pound. Using the speed ratios, as you can see, the torque for gears 3 and 4 were found to be 631.9 foot-pound, and for gear 5, it was found to be 3041 foot-pound. Using a gearbox with a height of 27 inches and a clearance and wall thickness of 1.5 inch, and using the equation down below, the minimum pitch diameter was found to be 5 teeth per inches. Using that information, the diameter for gear 2 and 4 were found to be 3.2 inch, and the diameter for gears 3 and 5 were found to be 15.4 inches.
Once known sizes and teeth number for the gears were determined, it was necessary to determine what material all the gears were going to be made out of. The first step in doing this was to calculate the wear stresses on the gears utilizing the sigma C equation for US customary units. We started with gear 4, which is transmitting the largest load with the smallest diameter and smallest number of teeth, and substituting our known transmitted load, face width of 2 inches and diameter of 3.2 inches, as well as the other constants that were given to us in the case study. It was determined that sigma for wear was 187,450 psi. From this sigma wear, an SC required was determined and compared to the tabulated value of 275,000 psi for SC for grade 3 carbonized and hardened steel. And so since this SC value was greater than our SC required, it was determined that grade 3 carbonized and hardened steel would be suitable to account for the wear stresses on gear 4. Next, it was necessary to calculate the factor of safety against wear, which was calculated using the equation seen on the left. And this factor of safety was determined to be 1.32, which was greater than our design requirement of 1.2 for the gears. After wear considerations, it was necessary to look at bending stresses utilizing the sigma equation seen on the left for US customary units. And again, substituting known values of our diametral pitch, face width, transmitted load, and various other constants. Sigma for bending was determined to be 52,371 psi. Sigma allowable was then calculated using the equation sigma allowable equals ST, which comes from the tables again of 75,000 PSI, as well as YN, which comes from the load rating of the gear. And utilizing these values, sigma allowable was determined to be a known value, and factor of safety was calculated with this known value, utilizing the known value and our sigma for bending, and it was determined that the factor of safety against bending was 1.332, which again is greater than 1.2 as required by our design requirements. Applying these previous steps to the remaining gears 2, 3, and 5, it was determined that grade 2 nitrided with a Brinell hardness of 300 was sufficient for gear 2. For gear 3, grade 1 nitrided with a Brinell hardness of 300 was sufficient. And for gear 5, grade 2 nitrided with a Brinell hardness of 300 was sufficient. And all of these factors of safety, both wear and bending, were greater than 1.2 as required.
All right, utilizing the equations on the top left corner where velocity, V is pitch line velocity, N is the gear speed, and H is the power input, we found the tangential and radial forces inputted at each gear. Using these forces, the shear moment diagram for each plane was then drawn and analyzed. And from the shear moment diagram, the reaction forces at each bearing was then calculated. The torque diagram was also found, and the maximum torque at each location was found as well. For the entire shaft, we chose a material of 1040 cold drawn steel, which has an ultimate tensile strength of 100 KSI and a yield strength of 84 KSI.
For shaft design, the group started with D5, which is the diameter underneath gear 4, which again is the gear that transmits the most load. Our initial assumption for shaft material was 1020 cold drawn, and utilizing Goodman fatigue failure theory as seen in the equation for D, it was determined that D was needed to be 2.25 inches in diameter to satisfy our requirements. Factors of safety were then calculated around D5 at both the keyway and the retaining ring groove, as well as for D5 itself. And it was found that the keyway factor of safety dominated, as it was the smallest at 1.8, meaning that D5 has a factor of safety of 1.8 against fatigue. Yielding was also checked at this location and was determined to be 3.1, and both of these factors of safeties are greater than the design requirement of 1.5 for our shaft. Although it should be noted that during keyway factor of safety calculation, the factor of safety for the keyway fell below our design requirement with a material of 1020 cold drawn, at which point our material was then upgraded to 1050 cold drawn, while we kept our initial diameter size of 2.25 inches, as this provides extra rigidity for the shaft. And utilizing a big D over a little d ratio of 1.2, diameter 4 was calculated to be 3 inches. And again, fatigue and yielding factors of safety were checked, and they were 6.8 and 12 respectively.
All right, next, the diameter 7 was calculated using a standard R over D value of 0.02 and a big D over small d value of a 1.4. KT was found to be 2.7. Using these equations, the diameter 7 was found to be 1.625 inches, while diameter 6 was 2.25 inches. However, it is important to note that the factor of safety of diameter 7 is too close to the required one. Therefore, it might be changed with the bearing size, bore size, depending if it's needed or not. Now that the entire geometry of the shaft is known, an FEA analysis was done to find the maximum deflection at each point. As you can see, the maximum deflection is where the gears are gonna be, and it's highlighted in red. The maximum deflection was found to be 0.03 of an inch, which is acceptable since we have a pitch of 5, and the maximum deflection for a pitch of 5 in a gear should be 1/100th of an inch.
Now for the bearing selection, looking into the analysis of bearing A and B that sit at the edge of the shaft on both ends. Starting with bearing A, we added the reactions at the corresponding part of the shaft. The force calculated was 868 newtons, and with the force and the XD, we found that the catalog rating was 10,373 pounds. From there, we were able to find a corresponding deep groove ball bearing on an online catalog, where you can see all of the dimensions corresponding to that bearing on the left side of the slide. That is where we found the inner diameter that is perfectly suited for our shaft at that point. For the following bearing B, we used the same method and found that the force was much higher than bearing A at 3,543 newtons, and with a catalog number life of 33,034 pounds. Looking at the online catalog, we determined that the load was a little bit too high for the groove ball bearing, so instead we went with a cylindrical roller bearing. The bearing will be much more suitable for the forces at that point, but on the online catalog, we see that the bore diameter is much larger than the shaft that we determined at that point, so we should adjust the shaft accordingly. Moving on to the key selection, using the material 1020 cold drawn, which gives us the ultimate strength and the yield strength. Choosing a factor of safety 2 and a standard case of a square key, we were able to use the shaft diameter to find the thickness of the key. Then, using the equations on this slide, we were able to find the force of the key, and using the force and the design factor of safety, we were able to find the L. This would give us all the dimensions we need for the key of our shaft. To see all of the steps that we did in order to come to all of these conclusions, we have a link at the bottom of the slide and also at the description if you would like to take a more closer in-depth look. And with that, I conclude the presentation, and I just want to take this moment to thank you on behalf of our team for a good semester.